Hello students, in this video I will talk about experiment number 6 of Applied Physics UPH004 course. The title of the experiment is Study and Proof of Malus Law in Polarization. As far as Malus Law is concerned, it says that when unpolarized light is fed on a polarizer, it becomes polarized, and then subsequently if this polarized light is fed on the analyzer, then depending upon the orientation of the analyzer, one can find the intensity of the outgoing beam. So this is what we will analyze as far as this particular experiment is concerned. The contents which I will be covering in this particular experiment are introduction, apparatus, then of course I will talk about the principle in reference to which this experiment is performed. I'll be giving you some basic idea of the procedure, and then of course results and precautions. As far as the polarization is concerned, a light wave vibrating in more than one plane is referred as unpolarized light, and the light emitted by sun, a lamp or a candle flame is unpolarized. So please keep that in mind. So this the non-polarized component of the light, and say this is a polaroid, and this polaroid is converting unpolarized light into the polarized form. The polarized waves are light waves in which vibrations occur in single plane, and the process of transforming unpolarized light into polarized light is called as polarization. So you can see, if a unpolarized signal is fed on the polarizer, then of course we get the polarized light, and say this is the second polarizer. So depending upon the direction of the axis of the analyzer, we'll be having either no light here or full light here. Say for example, in this case the second polarizer is perpendicular to the first polarizer, so you get zero light as a output. However, in the second case it is making an angle theta less than 90 degree with the first polarizer, so you see some light. As far as the conversion of unpolarized signal into the polarized form is concerned, we can do it by various methods. That means convert the unpolarized signal into polarized form by reflection, refraction, double refraction, selective absorption, scattering, etc. So this is a small video which shows that electric and magnetic components are perpendicular to each other, and of course both electric and magnetic field vectors of the electromagnetic light, they propagate in a direction perpendicular to that of direction of propagation. So this is how the ordinary light looks like. You can see the electric and magnetic components are perpendicular to each, and of course both E and B are perpendicular to the direction of propagation of the light waves. So when this unpolarized light is fed on the polarizer, say something like this, it becomes polarized. According to Malus Law, when plane polarized light is incident on the analyzer, the intensity of the light transmitted by the analyzer is directly proportional to the square of cosine of angle between transmission axis of the analyzer and the polarizer. So you see, this is a polarizer, this is the analyzer. So if the polarizer and analyzer make an angle theta with each other, say this is the vertical axis of the polarizer, this is the vertical axis of the analyzer, and say they make an angle theta with each other, then the intensity of the light which you get from the analyzer will read as I naught cos square theta, where I is the intensity of the light after leaving the second polaroid, I naught is the intensity of light before entering the second polaroid, and theta is the angle between the two polarides. A little bit further analysis of this. Suppose if theta, that is the angle between polarizer and analyzer, is 0, the second polarizer is aligned with the first polarizer and the value of cos square theta becomes 1, that is maximum. Therefore, the intensity transmitted by the second filter is equal to the light intensity that passes through the first filter. This case will allow maximum intensity to pass through. So you will be having maximum intensity at theta equal to 0, theta equal to pi, theta equal to 2 pi, and so on and so forth. On the other hand, if theta is 90 degree, that means the second polarizer, which we call as analyzer, is oriented perpendicular to the plane of polarization of the first filter. And cos square theta, that is cos square 90 degree, becomes 0. Which means that no light is transmitted through the second filter. This case allows minimum or 0 intensity to pass through, and this scenario will be operating when theta becomes pi by 2, 3 pi by 2, and so on and so forth. So the major apparatus which we use in this experiment is, of course, we have the lamp source, then of course polarizer, analyzer, LDR sensor, optical bench, power supply, and the multimeter. I'll just try to give you some idea how this experimental setup looks like. So you have an ordinary lamp which can give me variable intensity depending upon wherever I set it. And then say this is polarizer, say this is analyzer, this is the LDR sensor in which the signal from the analyzer is fed. Few more components, say for example you have the convex lens that is used to focus the polarized beam which is coming out of the second polarizer. Then of course we have two power supplies, one for the lamp and another for the LDR. Then of course one can use the multimeter to get the current from the LDR sensor. As far as the light intensity is concerned, we use the ordinary lamp for the formation of unpolarized light. So we get light of variable intensity. I can change it from say lower intensity to the higher intensity, and the polarizer analyzers, they look something like this. Polarizer and analyzers are used with inclination angle say from 0 to 90 degree. So these are the arrows. Please see here, this is one arrow here, another arrow here. So if I put both the arrows at 0, that means both the polarizer and analyzer, they are parallel to each other. So if I want to incline the analyzer with respect to the polarizer, I can keep on rotating it say from this position with a difference of say 10 to 15 degrees. So 10 degree, 15 degree, 20 degree, 30 degree, and so on and so forth. I can vary it from 0 to 90 degree and then see the output of my current which I see through the LDR. As far as the LDR sensor is concerned, we call it as light dependent resistor, or we also call it as photoresistor. It is the light sensitive device most often used to indicate the presence or absence of light or to measure the light intensity. This is how it looks like. LDRs are sensitive to the wavelength of the light used, and please do remember that it is basically a photocell that works on the principle of photoconductivity. Photoconductivity is nothing but an optical phenomena in which the material conductivity reduces when light is absorbed by it. We also use the convex lens primarily to focus the incoming beam from analyzer to the LDR sensor. Of course, we use the optical bench. Optical bench is used to adjust the alignment of various optical equipments. You can do the horizontal alignment, of course you can do the vertical alignment. Please do remember that optical bench consists of long rigid base with a linear scale applied to it. Holders for the light sources, lenses, and screens are placed on the apparatus so that image formation can be observed. So initially suppose my polarizer and analyzer, they are parallel to each other. That means the angle between the polarizer and analyzer is 0 degree. Then of course the maximum light will be transmitted on the LDR, and I'll see the maximum current. Suppose this is the current which I read. Then of course, suppose if I rotate my analyzer with a angle of 15 degree with respect to the polarizer, then of course the intensity of the light which falls on LDR will decrease, and consequently the current will also reduce. So instead of 9.14, now at 15 degree it becomes 8.76. Then suppose I change this angle from 15 degree to 30 degree, it reduces further to 7.64. And similarly, the moment I make it say 90 degree, my intensity becomes very, very small, say close to 0. So I can, this is how it looks like. My current increases as a function of cos square theta. Then similarly, I can plot the current as a function of the angle between polarizer and analyzer, and this is how it looks. The percentage error, of course, I can calculate using this particular expression. Say for example, in this case, I naught cos square theta is this number and summation of I say this number, so I can calculate the percentage error. Some sources of error and precautions are to be kept in mind. Say for example, experiment must be performed in the dark room because otherwise you will not be have the proper impact on the LDR, because the daylight will also be interfering with it. Of course, lamp, polarizer, analyzer should be aligned linearly. The position of polarizer should not be disturbed. Note all the readings and plot the graphs carefully. I acknowledge the sites for the figures which I have used in this particular video. Thank you very much.